That's thumbs up. Even radio, you didn't.
No, I don't use it either, but I am not good at the radios. Hi, welcome. So as you may notice, this is not bot. Um, but thanks for coming. Unfortunately, the original speaker had to cancel, so my backup speaker was on hand to jump in. So I actually don't have it written down, so I'm gonna do it from memory, or I'll read your screen. But yeah, some quick. Yeah, I got you. Some quick announcements. There is one more talk after this, and then after that is closing ceremonies in this room. If you're doing any contests or you're looking to pick up any swag or kits or whatever from all the various vendors and tables, I would recommend doing that sooner rather than later, as most of them are closing up. I think most of the contests that you guys were participating in are in the last phases of wrapping up. So frankly, those people are probably furiously typing and not hearing the talk. But coming up next is Quantum Computing Basics with Merlin. He'll tell you all about it. It's really
Yes, thank you for coming. As mentioned, this is a backup talk, so it's going to be a little rough, but definitely I've got a bit of experience in this area, and so hopefully if you don't know much about quantum computers or quantum cryptography, then you'll learn some stuff here. Oh, thank you. Everyone hear me better now? Awesome. So yeah, as I was saying, this is a little rough. I haven't practiced this talk, but I do have experience in the area of quantum cryptography. And so if you want to learn about quantum computing and quantum cryptography and how that applies to the real world, then you'll do that here. All right. So basically, we're talking about quantum computers and what exactly they do, because generally some people have a misconception that a quantum computer, once it works, will be faster than a classical computer for all algorithms, and that is not the case. It's only certain algorithms where a quantum computer can actually beat a classical computer. However, in those certain algorithms, it beats the pants off of it. So that's the main mechanism of how it works. We'll dive into a bit more in depth here. So I'm not sure. Let's see. Oh, yeah, that was for the demo contest. So generally, we've got logical and physical qubits. So a quantum computer is looking at generally the spin of an electron, and that's going to be your physical qubit. The spin is visualized as like a circle, a two-dimensional circle, and then they pick like an orientation, say the top of the circle or the bottom of the circle, and that's what counts as 0 or 1. So anything kind of in between, they look at where it's mostly pointing, and they say, hey, that's what my qubit is. It equals that value. So that's a logical qubit, is like one single electron. Or sorry, that's a physical qubit. Unfortunately, when dealing with quantum computers, there's also a bunch of error correction that must be done. There's decoherence and all these other problems that cause essentially the reliability of getting that value to go down, which forces you to have more physical qubits for every logical qubit. I don't know the exact ratios that are state of the art today. I do know that recently Google came out with some research that vastly reduced how many physical qubits are needed to make a logical qubit due to some advances in error correction. But in general, it's at least probably 10 to hundreds of physical qubits to make one logical qubit. So the way that it actually makes it faster for certain algorithms is through superposition and entanglement. So if you were to play a game like a poker-like game, say Balatro, where you might have a very strange poker hand available to you, and you were to sort those cards by their rank, you can see up on here on the screen, on either end, there are 9s. And when it flips all the cards, in the middle, they're all 9s. So that is a hand of 10 cards. But because of how they're sorted and because of how they are entangled in a quantum state, it's possible to only measure the two outside cards and say, oh, these two outside cards are a 9 and everything is sorted. Therefore, I know that the inner 8 cards are also 9s. And so if you think about that kind of concept and scale it up massively, that's how you can use a quantum computer to gain efficiency over a classical computer. If you have thousands of these things that are entangled such that reading one will let you infer the value of the other, you can scale that out massively, especially the more logical qubits that you have available to you. Let's see. Just make sure I'm covering most of the basics there. So yeah, in a similar fashion, sorry. This is a similar situation being displayed on here, except instead of it all being 9s, all of the cards are hearts. And again, this kind of is just a visualization of quantum superposition and entanglement and how you can use that information to gain more information without paying the cost of the computation. All right. So there's various ways to mathematically represent qubits. Generally, from a high level, you can think of a quantum system as a vector because the square root of the sum of all of the squares and the probabilities in the system must add up to 1. So no matter how many qubits you have, you must add all of those together to get a value from 0 to 1, 1 being everything is activated. And I guess the kind of important point to get across here is tying it back to why we have to deal with all the error correction and such. We're not just spinning one electron to see where it lands to figure out a qubit. If we have 1,000 qubits, they have to. Okay, sorry. Let me take it back a little bit. If we have a system with 2 qubits, you have a 50% chance to hit either one, more or less. If you had 100, you would need a 1% chance to say that it's activated. So it goes from being 0 to 1 to being 0 to n for however many qubits you have, which makes it all that much more complicated. The more qubits you add, you have to get that much more precise with controlling your electrons. And the way that they control the electrons is apparently with magnets. I almost said magic. Magnets are not magic, but they're close. So they use magnetic fields to bias the spin of the electron within the tiny range that it needs to be. But we're talking about single electrons, and we're talking about potentially thousands of them that we're monitoring and manipulating. And that is why quantum computers are generally very large and need to be supercooled, because everything needs to be isolated to help lower those physical errors, because you have to be so precise. So as I said, only certain problem.
Let's see.
There we go. Okay. A common representation for notation for qubits is a bar and then a subscript and then a greater than sign. So here you can see qubit 0, qubit 1 on the top row, and then on the bottom I show addition of various qubits, which is that bar, 0, subscript, greater than, and then plus in each subscript. So as I was trying to explain the number of qubits you have in the system greatly affects the math involved. And so it's a nice little shorthand for it. So 2 qubits have 4 possible outcomes. It's like a 4-sided die that has faces of 0, 0, 0, 1, 1, 0, and 1, 1. And that's generally the notation. The math gets pretty hairy from there. It involves a lot of stuff with probability, obviously. So to actually get really deep into it, you have to start learning advanced statistics and probability. And I don't know that, so I'm not going to try to pretend I do. So this is some random factoid that I think Jim and I tried to put together, but I have an older one that I know is more realistic. And basically, right now, no one has a working quantum computer that can break classical cryptography. So everyone's working on estimations of how many logical qubits they might need. So a number that I heard at the end of 2025 was that for Shor's algorithm to beat it, you would need, sorry, I'm looking through my notes here. There we go. You would need somewhere on the order of 4,000 to 10,000 qubits to crack RSA. And again, near the end of 2025, some of the largest publicly known systems only had 1,000 logical qubits available. So there's still some runway. All right. So hopefully that's a good sense of the basics, especially if you've never really heard of quantum computers or post-quantum cryptography. We're not going to go too much more in depth on that side. Now we're going to talk a good bit about post-quantum cryptography standards. So on that front, the one I'm most familiar with is the North American side of things. So for 8 years, NIST ran a post-quantum cryptography algorithm shootout where they pitted different algorithms against each other. So a researcher or maybe a cryptographer at a company, maybe it could, but a lot of it was university people. They would suggest an algorithm, they would write a paper, they would put it out, and then the other teams would attack them and then write papers about how they broke them. And this went on and on and on for 8 years until we got what are the current standards, which there's two like main ones, which are both based on the same type of cryptography, and there's an alternate that is for each section. And I should probably explain, in case you're not aware, the 2 types of algorithms generally there. So there are key encapsulation algorithms and signing algorithms, essentially. Those are the 2 main methodologies, because when it comes to post-quantum cryptography, your standard symmetric AES with 256 bits or more is considered post-quantum safe by the US government and basically everyone else who's currently researching. Because again, like I said at the beginning, quantum computers only make certain algorithms very fast. They don't make every algorithm very fast. So for a high enough number of bits of AES, there's no way that a quantum computer can give you an advantage. It just doesn't have the algorithm to break it. So key encapsulation methods are used to establish your symmetric key. And then obviously signing methods are used to sign data cryptographically and prove that it was written by, whatever public key it matches. It's still asynchronous cryptography. So in general, the winners for both categories were a type of algorithm called module lattice. These algorithms work on a theory called learning with errors, as well as the mathematics of a lattice. So you probably have heard of elliptic curve cryptography, which is one of the classical algorithms. That is based on elliptic curves and the problem of finding a point on that curve given some unknown information. That's essentially how it works. So as a similar metaphor, the way that lattices work is you take a certain point in space and through some transformations in the complex plane, because it involves complex numbers and imaginary numbers, which are complex numbers. I'm just repeating myself. And puts another point based on that transformation on that plane. And then it adds some random error to it, which makes it a heck of a lot harder to calculate where the actual lattice definition is when you're given the candidate point that you're trying to validate. So again, just to kind of bring it back home, the elliptic curve, we're looking at a curve and trying to find a point on it. With the lattice, there's some super secret formula that says I have a point here, and based on my formula, there'll be another one here, and another one here, and another one here. And if you continue that out in all directions, you'll get a lattice. Like it'll look like cross-hatched things if you connected all the lines, it'd be a very regular pattern. But very regular patterns are easy to reverse mathematically. And so that's why they came up with this learning with errors thing, which added some uncertainty to the process. And because of that, when you're doing the math on these things, the actual algorithms involve recalculating things multiple times because some of your values check to be essentially wrong because it's random. There's, there's errors and stuff. So you have to do things in a loop and just kind of find the point iteratively. And that's a much harder problem because it doesn't have periodicity, which is essentially how the quantum algorithms end up breaking classical cryptography. So let's see. What else do I have on that? Non-dual lattice. Oh, yes. So I don't know the numbers offhand, and I should have prepared them, so I'm sorry. But I believe in America, they're all under the FIPS standards, and I want to say it's like FIPS 203, FIPS 204, somewhere in that range is the module lattice type stuff. There are other approaches as well, though. As I said, they pick an alternate because an important thing here is with all this new post-quantum cryptography, it's all very new. And as we know, most new algorithms aren't necessarily as good as we hope. I was actually having an interesting conversation earlier with someone here, and we were discussing whether or not to use a hybrid scheme where you use both a classical algorithm with a quantum algorithm. And that's to hedge on whether or not your quantum algorithm is safe. The counter argument to that is that A, you're adding complexity, and B, there might be some unknown interactions between the two algorithms where one weakens the other. So, because it's just as new, basically, it makes it a new scheme by definition. So because of that, for the NIST standards, they picked a couple alternate schemes. One of them I know a bit about, and that is called Shinx Plus. So the kind of interesting thing about that one, instead of being based on like a curve or a lattice or any of that, it's based on Merkle trees, which if you're into cryptocurrency, you might have heard a little bit about that. Most of them are signed with a Merkle tree. That's how their blocks are signed. And it's it's actually a pseudo random number generator where your key is actually the seed to make 2 to the 64, which is a really big number, trees of trees that they essentially call a forest. And that gives you a bunch of little tiny pieces of cryptographic information that can be used to put together a signature one time that can be validated. You're basically saying, yeah, I'm using, tree 2 to the 32nd, number 1, 2, 3, 4, 5, 6, 7, this little piece of key. And so from that giant, huge key space, you can reliably generate signatures without giving away your entire key material. I want to go too in depth on it, but that goes from previous research where people tried to use, say, simple trees, simple signatures where they just had, a big long string of bits, and they're like, I'll sign on these bits here repeatedly, and then the more things you sign with it, the more that people get pieces of your signature, the easier it is for them to reconstruct it and then crack the rest, and then now they can sign things as you. So the way they dealt with that is to literally just make the key space so large that it's just not possible for someone to collect all the pieces, even if you're signing stuff constantly. There is also another one that got eliminated. It was called Rainbow, and it was based on multivariate polynomials. But the Sphinx team that I just was talking about, they proved that Rainbow could be broken on a laptop in a weekend. And that was a big hullabaloo during the contest because they were ready to basically crown Rainbow as a winner. And then the other team was like, nope. So there's just a lot of interesting stuff around that contest. It's worth checking out and kind of reading about some of the exploits of the participants because it was a full-on offense versus defense thing from team to team. Also, I don't know, maybe you'll be interested to know that the code names for MLChem and MLDSA, which are the module lattice ones I talked about that won the primary, they were originally called Crystals Kyber and Crystals Dilithium. Crystals was an acronym that composed of Cryptographic Suite for Algebraic Lattices. And it ended up winning out due to its basically it resisted all attacks for all 8 years. It went through a couple iterations to make it a little stronger, but that's to be expected. And yeah, MLDSA, MLChem, that's in America the most standardized things. And I think they're getting similar standards in Europe for it, but I don't offhand know how they're designated there. I do know that HTTPS security, TLS rather, I should say, TLS 1.3, I believe it is, already also has a post-quantum algorithm, and it's based on those module lattice type constructions. Let's see. Where are we in the presentation? Okay, yeah. So I was pretty close on my guesses there. So MLChem is FIPS 203 if you would like to look that up. FIPS 204 is MLDSA. And then I think that FIPS 205 is that other thing I was talking about. They renamed it from Sphinx to something else, I believe, but I think that's what that SLH DSA is. Sorry, I got a little ahead of the slides. Yes. So, yeah, there are some standardization efforts in Germany, again, based on the modular lattice type stuff. And in America, the government, through this program, the National Security Algorithm Suite, CNSA 2.0, they're requiring basically that any government contractor or agency should be using post-quantum cryptography algorithms by 2030. And I'll just repeat a thing that I heard at a talk many years ago that rung true with me. And it's essentially, if the government is telling you that within a few years you should probably not be using some type of cryptography, then there's at least some chance that somewhere they think they have something that can break it. So even if there isn't any publicly known quantum computer right now that can break this stuff, maybe there will be in 5 years, 4 years now at this point, because we're 2026 now. So just keep that in mind. And if you do deal with any kind of cryptographic infrastructure, dealing with key signing or encryption for your organization, consider some post-quantum cryptography. So yeah, I've tried a couple different tools for working with Python post-quantum algorithms and post-quantum cryptography and algorithms. So there's a Python library called PyCA that's essentially like OpenSSL in Python, you could call it. And they have a whole bunch of the cryptographic primitives in there. So if you need to use it in your own programs, that's possibly one source where you can get it. Also, OpenSSL, as I mentioned, has it, and there's Python libraries and such for that. But generally, also, there's a bunch of Python libraries out there for simulating quantum circuits, so that you can essentially take Shor's algorithm, which is the most famous one, the one that, if we ever get a working quantum computer, will be able to break RSA. That is what I would recommend if you want to learn more about it, is get one of those quantum simulators and run some quantum Python on your quantum simulator and run Shor's algorithm. I would have hoped to have an example of it, but as I said, talk's a little rough. I didn't get through it. If you guys want to hear a little bit more, though, I can give you a little bit more info on how Shor's algorithm works, in case anyone does want that. Give me one. Okay, I see a nod. Okay. So let's see. All right. So I'll just explain the high-level algorithm to start. So Shor's algorithm starts with an integer x, and you want to find some power of r such that x to the r is equal to 1 mod n. R, and to be clear, those are the math. That's the math for most basic like RSA type of things. That's the formula that gets you your runtime secret key based on like your private key and their public key or vice versa. It's that math formula that takes your big prime number and their prime number and mixes it together. So that's all that I was saying, was we're starting with some integer x within that formula. Next, we look at, again, it ends in mod n. We look for some number x that shares a factor with n. We find the factors of n, p, and q. Then we find what's called the magic power of n, which is the lowest common multiple of p minus 1 and q minus 1. And then we crack the RSA. And since, again, Shor's algorithm is it's a quantum algorithm, it's going to be doing that by relying on entanglement so that it can figure out some smaller subset of the values and then extrapolate to the rest. That's essentially the most layman way I can put for how it works. And yeah, I would say that's probably about all the overview I have available. Let's see if I have anything. I got the card matrix that wasn't in the demo last night, so cool. And then yeah, greets. And then if anyone does have any questions, I can answer one or two. Otherwise, yes, sir.
The how we can tell that
Let me see if I wrote notes on that real quick. But all that I know that I had written was that the other team cracked it.
sure.
Oh, that's a good point. Thank you. So he asked about the rainbow algorithm that I mentioned that failed the competition. He asked how specifically it had failed, and I'll see if I do have internets. If in one search I can find it. If not, all right, no worries. So, in February 2022, Ward Bulens published a paper, Breaking Rainbow Takes a Weekend on a Laptop. It was due to an intersection attack because it was previously believed the rainbow band separation attack that was used. Oh, I see. They improved on a previous analysis that people thought wasn't a strong enough attack, and the creators had updated parameters like base numbers into the system, which makes it a new scheme and actually made it easier to break. I don't have any details on exactly why though, sorry. Yeah, so the question is like for on a Python simulated quantum computer, since it's not on a real quantum computer, do we pretty much got to keep it to very toy examples? And I think the answer is yes, because it takes exponentially more computation on the classical, and that's kind of why one of the criticisms of Shor's algorithm is they haven't demonstrated a device that can use it to factor the number 15. And factoring a very large number on your own laptop in a simulation, probably going to take quite a while, maybe even longer than the heat death of the universe, according to some people. So it's a hard problem. But I firmly stand by, if the government is telling us, hey, maybe change these algorithms by this date, I feel like someone has some attack. Maybe it's not even quantum. Maybe it's some other attack. But we potentially just need to move algorithms because we need to. So that's my stance. All right, thank you. If you have any more questions, you can definitely talk to me. I'll be down in a minute. But thank you for coming. Sorry it was so rough. Thank you for bearing with me. I really appreciate it and hope you guys have a great day.